Okay, good morning everyone. A couple of quick announcements. So there is no quiz due this Tuesday, okay, as we have mentioned before in the last lecture. There is also no homework due this week. I'm going to have only one last homework assignment. Okay, that will be incorporating combined learning, 3D, more 3D problems. After I post the solutions for your homework 9 and 10 in the next couple of days. Then we will have problems on what we are covering right now, which is plane stress, and we'll go on to what is called as plane strain as well. I might try to touch upon the topic of beam bending. I might not go too in-depth into that because, as you see, we don't have that many lectures left. Okay, but I still post the lecture notes so that people who might use it later on can maybe use it. Okay. One of my biggest beefs with mechanics of materials is this is a course. This entire sequence is a course that when I was a student, it was taught over a period of 1 year. So we are trying to compact everything down and feed it to you in a period of 3 to 4 months. And because of that, the speed of teaching has to be very fast. And if the speed of teaching is fast, there is a chance that the majority of the class might get left behind. So what I have done is I have slowed down as much as I can in terms of what I can cover. I believe that the topics that we are covering in this class are the most useful to you as you go further down. Okay? Additional topics, if you know what we are doing now, if you know this well, additional topics should be fairly straightforward to you. It should not be requiring any more deeper thought than what we are doing right now. So that is my intention and my hope. Okay? Hopefully, if you do have questions in the future, you are more than welcome to stop by my office for other things too. Okay? All right. I will have one last homework assignment, which will be due next week. I will have one last quiz, which will be due on the last day of the class. It's not a quiz where you're going to solve a problem. It's a quiz where you'll be filling out your online SCIs. Okay, so 3 points. If you do it, whether you do it or not, I just need your word that you've done. I'm not going to force you to write stuff, but I appreciate honest feedback. If you feel like there are aspects of this course that are good, you can let me know. If you find aspects of the course that are kind of disturbing, certainly please let me know. I'll be more than happy to change course. This is a course that is closest to my heart. Unfortunately, the number of people in class doesn't attest to it, but I can only do so much other than do a song and a dance here. Okay, but we will continue. Okay. What I want to do today is, before I go on, and I have posted pre-lecture slides. Some of the more complicated figures are available in pre-lecture slides. I will draw them along as we go. But before that, I want to give a very brief overview of what we have done so far and where you might probably start applying all of these things. And then I'll talk about plane stress and plane strain and all these other things that we plan to talk about. Okay? So mechanics of materials. What you typically do, what are the steps that are involved in solving a problem is the following. First of all, why do you study mechanics of materials? Is because things break, things fail. One has to make sure that whatever you design does not break or fail before its due date. And everything is going to break at some point. Nothing is immortal. but you don't want it to break right away, or you want it to give visible signs of failure as you reach that failure point. Okay, so that's where the majority of design is oriented towards. So to do that, you need to solve the problem, understand the internal stresses and strains that are caused as a function of the external loads, find out locations that are critical, and try to make sure that the design measures that you take assuage that question. Okay? So here are the steps you typically take in solving a problem. You've done this all semester long. I just want to reiterate that message. Okay? First step in solving any problem is you draw the free body diagram, you do the static analysis. Right? You find out the reaction forces, reaction moments, and so on. Some of forces, some of moments. Right? All of them in vector notation. Then the next step is this. So the static ship has sailed. You go to the mechanics part of the problem. In certain problems, because of the fact that the load varies in very strange ways, it is not possible to know where the critical location in this body is. Okay, where is the location where the stresses are the largest? I just cannot inspect the problem and then tell you, right? In certain cases, there is a dead giveaway. Maybe there is a crack. Obviously, the stresses there are going to be the largest. Perhaps not in many other problems. So the second step is to assess critical locations, which are locations where the internal forces are the largest, or the internal moments are the largest. Okay? So assess what is a critical location? The location where the internal forces and moments, or the internal torques, if you have a torsional load, these are the largest. Locations of Vmax, Mmax, tau internal max, all of these are internal loadings, even the normal forces, and max, I should say T max, not tau max, sorry. Okay, so these are all internal loads. In many problems you can inspect it and do it, but in most problems you have to do it step by step. When we did problems in torsion, we had to section it between every two discontinuities and figure out, okay, here is where the internal torque is the maximum. Right? If you're doing problems on forces such as Vmax and Mmax, you have to draw the shear force and bending. So this is typically done by drawing the shear force diagram, bending moment diagram. If you have axial forces, you can inspect by sectioning off between every two discontinuities to see where the largest axial force is. Okay, so those are all things that we typically do. Once you assess the critical location, once you figure it out, or this could also be visible regions, or it could be locations where these are the maximum. If it's a visibly viable region, then you will see that there is a crack or some kind of a discontinuity going on there. Okay. The third step is, at that critical location on the body, you have to find the stresses. Obtain these stresses. At the critical location. This is a tricky part. Why? This is because the location where the shear stress is a maximum, due to either the torque or the shear force, is not necessarily the location where the bending stress is the maximum. Or likewise, the location where the normal force is a maximum along the length of a body need not be the location where some of the other things are a maximum. So this might have to be done at multiple locations where the stresses are maximum. Okay, so probably multiple locations, which is what we've been doing, right? And then we typically say, okay, on that location along the length of the body, look at the cross section, find out points on the cross section that could be critical. So this is location along the length of the body. And once you figure out, okay, these are all the critical locations based on where Vmax is the maximum or M is the maximum, then you figure out, okay, on the cross section, what are the maximum points of stress this feeds into. Points of maximum stress. Cross section, if you're doing a problem on torsion, any point on the outermost circumference is a point of maximum shear stress. If you're doing a problem on bending moments, largest distance away from the neutral axis, that's the point where the bending stress is the maximum. If you're doing shear stresses, transverse shear stress, which is a VQ by IT formula, then neutral axis is your culprit. So these are all the locations that you're interested in typically, right? Then you draw the state of stress at those locations on a volume element, write out the stress matrix. This is the most important part of the problem because this is what is going to feed into failure theories, which we will not be doing here, but you're seeing a little bit of it here. Draw the volume element. And then write the stress matrix. In writing the stress matrix, there is actually a sign convention which I have purposely not introduced yet. Probably never will, but I will talk about a little bit of it today, okay? Because it can be confusing. But once you write out the stress matrix, then the question becomes, okay, can I take this problem and simplify it in certain ways? Indeed I can. If I have a problem where the body is very long and the thickness is very small, then I can simplify it as a plane stress problem. That is, all the stresses out of the plane of the body, they are negligible. Okay, so that's what we are doing now. So this is step number 6. Right, so if you have a plane stress condition, this is mostly applicable for bodies that are very thin. Okay, you can ignore the stress components out of the plane of the body. Okay, so for very thin bodies, ignore the stress components out of the plane of the body. As an example, we looked at things last time. Let's say this is a body, thin body, long, but very thin, x-axis, y-axis. The z-axis is the axis that is out of plane here. I can as easily label these axes as z, x and y, and the y-axis will be out of plane. So please be careful. Just because this is labeled as z doesn't mean it has to be z all the time. Axis is for convenience. Okay? So in this problem I can ignore all the stress components which have the subscript z on them. So ignore sigma zz, tau yz, tau xz. And then my stress matrix at any point, it may not be fully populated, but this is the maximum it can have. So the stress matrix at any point becomes the following. Sigma xx, tau xy, tau xy, and sigma yy. This is a symmetric matrix. And this is what we've been looking at last time. Okay, so the plane stress condition. And I want to very quickly talk about the sign convention that is used for the plane stress condition. Are there any questions so far? It's been a monologue for the past 10 minutes. Any questions, please? Okay. There is also something called as a plane strain condition, which I'm going to explain in a minute, but before that I'll slide this up. Alright, so the plane stress condition, we use the following sign convention. So watch this carefully. This is a little different from what I told you last time. That's also a possibility, but the book is using the following sign convention. I want to stick to what the book does, okay? Because there are people who might look at the book and then get confused about this. So this is the sign convention for stresses. For plane stress. Okay, based on the book. A rectangle. Call any axis as x and y. Typically the convention is that the horizontal axis is x, the vertical is y. X axis. This is the y axis. Now watch this. Once you have decided that you're going to call this as the positive x axis and the positive y axis, now the area normal to this side is along the direction of the positive x axis. Correct? If I draw an area normal, okay, so that's going to be n hat, okay, that's the area normal, and this is pointing in the x direction. This is a positive sign. Then, if that is the case, according to the sign convention for the stresses, all the stresses must be pointing along the direction of the positive axis. So I'm going to have sigma xx pointing along the positive x-axis. Tau xy will be pointing up, as opposed to what I had drawn previously, which is also completely fine as long as you stick with one particular convention or the other. Okay? So in this case, tau xy is pointing vertically up. So once again, reiterating what I'm saying here, I set up my axes x and y. Good. Then I figure out, okay, if I draw an area normal on this side versus the other side, the area normal on the right side is positive because it's pointing along the positive x-axis. The area normal is negative on the left side, it is pointing along the negative x-axis. So on the side that has the positive area normal, according to the sign convention, the positive stresses will be pointing along the x-axis and along the y-axis. Once I figured this out, everything is history, because here I have to have a balance. So this is going to be sigma xx. Tau xy on the other side will be pointing vertically down. Right? Counterbalancing what I'm seeing on the right side. Then on the top and the bottom, along the y-axis, positive y-axis, this is the positive area normal. Okay? So this is going to be sigma yy. Sigma yy, but because of the fact that the shear stress on the right face was pointing up, I need to have equal and opposite shear stresses on the top and the bottom, creating a couple moment. So they're going to be pointing this way and this way. Okay, so that's tau xy and tau xy. Does this make sense to everybody? And you can very well see that here the area normal is positive. The positive value of sigma yy is when it is pointing along the positive y. Tau xy naturally becomes positive and it's aligned with the positive x direction. And on the other side it's going to be pointing the other way. Okay? This can become confusing. Because what we earlier on said that was that if I'm drawing internal shear forces, they have to put this piece in a clockwise spin. So what is the truth here? The truth is that the problem will tell you what is the shear stress value and what is the proper sign of the shear stress. What is the proper direction? That is coming from solving the combined loading problem. And that is why when we wrote out the stress matrix, I did not put a sign for tau xy, but I said it's either pointing up or pointing down. And that is the thing that you need to keep in mind. Okay? Alright, so this is the plane stress condition. I want to briefly talk about plane strain and then go back to our lecture. Okay? So plane strain. It's a very weird condition, but it's very useful for bodies that are very, very, very long. Okay? For long bodies, for example, if you take a bridge, okay, a bridge is very long, right, most of the times. So if I look at a bridge, so let's say a bridge, for example, for such problems, it is possible to ignore the displacements in the length direction. Okay? We can ignore displacement of points on the body. Along the length direction. Okay, so if I draw a very long pipe, for example, I'm going to set up a set of a pair of axes. The planar axes will be y and x. Okay, then the z-axis is going to be the axis of symmetry of the pipe. This is the z-axis. What is the longest direction here? Typically the z direction, right? If the displacements are negligible, what is strain? Strain is nothing but displacement divided by the initial length of the body, in some sense. So which essentially means that if the displacements along the z direction are negligible, then all the strain components along the z direction are negligible, and like we had 6 stress components, we usually have a 6 strain components as well. So typically the strain can also be written in the form of a matrix. Okay? People in the maths department will be spinning their heads if I say this is a matrix. It's supposed to be a tensor of rank 2. More on that later, or maybe never. I'll tell you why there is a factor of 2 in the next lecture. Okay, so this is symmetric. YZ. And gamma XZ. Okay, so this is typically the strain matrix or the strain tensor, like we had the stress tensor. Okay. If I am assuming a state of plane strain where the body is much, much longer compared to its cross-sectional dimensions, then I can say that the strains along the length direction are negligible. Okay, so plane strain. Strain along the length direction is negligible. Typically, we call the length direction as a z direction, so which means all the strains that have a subscript of z will get knocked off. So this entire row will be 0, that entire column will be 0. You will have exactly something that looks like your plane stress matrix, but this is for strains. Okay, so this implies epsilon zz is 0, gamma xz is 0, gamma yz is 0. So, and one can cross out those rows and columns, and you reduce it to a 2 by 2 matrix, which is much easier to work with. And so you see that there are these two limiting situations. One is when I have a problem that is very thin, and then one is when I have a problem that's very thick. So if I draw them together side by side, this is plane stress. Okay, so this is a body that is very, very thin. If I draw the plane strain approximation, and in this particular situation the plane stress, that's the stress matrix that I'm working with. If I draw the plane strain side by side, here's what I get. So this is a very thin body. This is a thick or long body. If I have a thin body, it's a plane stress condition. It's a good approximation. If I have a thick or a long body, then a plane strain condition is a good approximation. Remember, both of them are approximations. Reality most probably will have a body that is between a very thin and a very thick body. Okay? So in that case it becomes a judgment call. Okay, by approximating it as a plane stress condition, what is the information that I lose out? I lose out information based on the stresses along the thin direction. If I'm assuming a plane strain condition, I lose out information on displacements along the thick direction. So can I live with one versus the other? That's typically the judgment call for the designer or the mechanics person. But these are the two categories of problems. Reality is always in between the two. Many problems can be assumed to be plane stress. Many problems can be assumed to be plane strain. And it is all just one giant simplification of something that is really complicated. Okay? Alright. So I'm going to start with this guy here and briefly revisit what we went through in class last time. But before that, is it okay if I can erase this panel here? Question?
Can I ask why in the matrix you're dividing by 2 and
Right. So we will talk about that when I start looking at more circle for strain in the next lecture. Because hang on to that thought. Yeah. We will cross that bridge. All right. So last class we started looking at failures, and we said, okay, there is a motivation for us to talk about the largest normal stresses and the largest shear stresses, right? So in the last class we looked at principal stresses. Right, these are stresses that are the largest normal stress values. Okay, so the largest. And we are going to limit ourselves to two-dimensional problems, right? Plane stress situation. In the plane stress situation, I'm going to have only two principal stresses, sigma 1 and sigma 2, right? They're going to be called sigma 1 and sigma 2. The planes that contain the principal stresses are free of shear. And you're going to see why today. Okay, we're going to motivate the discussion. But before that, sign convention. Typically the principal directions are called the 1 and the 2 directions. There are 3 principal stresses, but because I'm looking at a two-dimensional perspective of the three-dimensional problem, employing the plane stress approximation, I'm going to see only 2 principal stresses. The third one will be 0. Okay? So positive sign convention says this is sigma 1, sigma 1, sigma 2, sigma 2. So let's see why there are only normal stresses on this particular plane. I'm going to remove this panel here as well. This is a figure that you have in your PDF pre-lecture notes and notability thing as well, but I'm going to draw it out here. I'm going to consider a piece of chalk. Okay, let's take a piece of chalk. Okay, piece of chalk, brittle material, brittle. Okay, so if I take a piece of chalk and if I twist it, what's going to happen? Let's say I'm applying a torque. Okay, you see that the plane of failure is at an angle. We want to know what that angle is, and we want to know why it fails, or what is the reason for its failure. Okay, I'll tell you the reason for its failure. Experimentally determine that if I have a brittle material, the cause for its failure is tensile normal stresses. Okay, so a brittle material fails is due to principal stresses, due to maximum normal stresses. Most of the times the mechanism is tensile fracture, but in cases of compressive loading I can also have compressive fracture, but it takes a much larger compressive force to cause compressive fracture of brittle materials, because brittle materials are loosely packed. If I compress them, the molecules start moving closer to each other, so they become stronger in some sense. Okay, we spoke about this when we looked at material behavior a long time back. So I'm going to take a piece of chalk. Apply a torsional loading on that. Okay. This way, or let me choose it to be the other way because it's easier for me to draw. It's a torque. It's a torque that is applied. We know that a torque applied causes shear stress, but the failure of the brittle material is not due to shear stress, it is due to normal stresses. That is a weird thing about these materials. And so we want to figure out, okay, it fails, right? So perhaps the plane of failure, this is the plane of loading. The plane of failure is inclined, as you saw. Right, so this is the actual plane of failure. We want to figure out what this inclination is. Okay, so this is the plane of failure. We want to figure out what the inclination of this plane is, and we also want to figure out, okay, what is the largest stress value that causes failure. So what is the inclination? And what is the largest principal stress value or the normal stress value? Okay. To cause failure. We want to figure these things out. So everybody agrees with me that the plane of failure of the brittle material, if I apply a torsional loading, is an incline. When you just saw it, you can also break a couple of chalks after lecture. Now I'm going to do the following. I'm going to cut open this piece of chalk, look at the state of stress on an area element on the plane of loading. Okay? So section the chalk. Now what's the internal torque? The internal torque is the same at all points because there is only one set of torque applied, so there is no discontinuity here. So wherever I section this body on the plane of the loading, the torque is always going to be capital T. So there is no need for a torque diagram of some sort. Okay, so I break it open. Mind you, this is still the plane of loading. Here is the torque applied. and on the section that I have broken out, I'm going to draw an area element, say somewhere here. Okay, so here is my area element. What's the state of stress there? It is going to be a shear stress. The direction of the shear stress is going to track the direction of the torque that is applied, right? So if this is the torque that is applied, there is an internal torque here, which is equal to the externally applied torque, and so the direction of the shear stress is going to be pointing up. This is done. Remove that out, draw it as a volume element. You have all this in your notability files, just in case. Okay, so here is my volume element. Okay, I have the shear stress on this face, that's tau. That's due to the torque applied, one on the back face, equal and opposite, and on the top, and on the bottom. So far so good.